Question 4. So in this one, we're sort of combining a bit of mechanics and a bit of electricity, but it comes down to being mostly an electricity question. Got a boat being pulled up by an electric motor here, and we've already got a bit of information. It's a 24-volt battery that's doing the pulling. Negligible internal resistance, so we don't have any complexity there. And on the next page, we're given quite a lot of data. So we've got the current on the y-axis, and we've got time on the x-axis. We can see that right at the start, the current drives up and we get a current surge, which is normal for a lot of electrical devices like light bulbs and things like that, because when they're first turned on, they're still cold, their resistance is lower. So they experience an initial current surge, and as they heat up, that settles down to their working level. Exactly what we see here in a motor. Question 1 asks us to determine the total energy input by the battery in the first 200 milliseconds. So this student has correctly sort of marked off the area that's involved. The students also used the correct equation. Energy is power times time. And if we break power up into P equals IV, so energy is IV times time. Now at this point, we need to recognize that what we have on the graph up here is I and T. So this part is equal to the area of the graph. And this part, well, that's provided. It's just 24 volts. So we're going to work out the area of the graph, which, to be honest, is an incredibly annoying task to have to do. And we're going to multiply it by 24. So 1 mark is for working out the area of the graph, literally count squares, work out the value of 1 square, and multiply it by the number of squares. You're going to get 1 mark for multiplying it by 24, which quite a lot of you guys got, because it shows you've understood this relationship. And 1 mark will be for the answer itself. The answer is allowed to be in the range 220 up to 264. A few people had a go, but were a bit outside that range. So really, maybe a bit of practice and going back and seeing if you can get yourself in that range would be worthwhile. 1 or 2 people didn't notice that the time was in milliseconds, so caused themselves some problems there. And quite a few people just didn't use this algebraic relationship and were looking for other things that had current time, for example, maybe Q equals IT, and also saw the resistance equation used. So that's how we do this one. The next part, the student's done really well at, and overall though, there was quite a lot of error in this one. We're asked to determine the average efficiency of the motor during the first 200 seconds. Now just to remind you, in the last question, we worked out the total power that the motor used. So we actually already have, if we say that efficiency equals useful out over total in, well, we already have our total in from the previous question. Whatever number you came up with there, use it. If you didn't do the question and don't have an answer for that, the exam technique you need to apply here is just to make up a number on the last question. For example, on the previous question, write the number 10 and come over here and put 10 in here. It doesn't matter that your answer is going to be wrong. You'll be entitled to error carried forward marks on this one, which is actually what's happened here because the student didn't calculate the area and had the wrong answer. Okay, so the tricky bit in this question is working out the useful output. Now, if you remember, a boat is being pulled up a hill. So there are going to be 2 things gained. First of all, the boat's speed has increased, so we're going to have some kinetic energy. And second of all, it's been lifted up a hill, so it's also gained some gravitational energy. And if we look up here, the question's actually really unambiguous about it. Assume that all the useful energy output by the motor is transferred to kinetic energy and gravitational energy. Okay, so the useful bit is now kinetic and gravitational. So instead of useful, it's going to be kinetic energy plus gravitational energy. Now, quite a few people tried to equate these. So they found the kinetic energy equation and the gravitational energy equation and made them equal to each other. In this case, it's not a falling object. We've not turned gravitational energy into kinetic energy or vice versa. These types of energy have both been gained thanks to the motor. So we need to work them out individually. The student's done a great job at that, correctly worked out the gravitational energy and correctly worked out the kinetic energy. You can have a mark for doing either one of those actually. And then the next mark is for putting those into the efficiency equation, whatever your value of this is, and whatever your value of this is. If you've done that, you're on for a mark. And the last mark is for a correct answer using your own values. I've given this one the student because they've correctly worked it out using their own values. If you had the correct values, this will be 0.51 or 51%, but it could be anywhere in the range from about 47% up to about 56%. Okay. So this question over here is the one that I personally thought was really difficult. It was nice to see quite a lot of you guys getting some traction on this one, so well done. This student struggled with this question and I can absolutely understand why. So let's go through it step by step. Really, what they're asking for us to explain with reference to the properties of a thermistor and a fixed resistor why using a thermistor would be preferable. Now, I mean, I can easily answer that question because I know that a thermistor is a resistor whose resistance decreases as temperature increases. You know what? As long as you say that, you're going to get 1 mark. Whereas the resistance of the fixed resistor remains constant. Yeah, no mark for that. What we need to recognise here is that the reason why the thermistor is better is because once this whole circuit heats up to temperature, the total resistance of the circuit is going to be less because that thermistor's got hot and its resistance has now dropped, whereas it was previously the same resistance as the fixed resistor. So 1 mark for saying that the temperature in the thermistor is going to increase when the current is flowing. 1 mark for saying that increase in temperature means that the resistance of the thermistor is going to decrease. That's what a thermistor does. And 1 mark, final mark, for saying that that means, because it's got lower resistance, there's going to be less wasted power. There's going to be less wasted power in the circuit on the whole, because there's going to be less wasted power in the thermistor part of it. Okay. Now, they're very specific about saying less wasted power. I'm unsure whether I would be allowed to award less wasted energy, but to be honest, that one didn't quite come up. You could also have talked about the fact that because its resistance was lower, less of the PD will be used across it, so there's less PD dropped across the motor. But yeah, okay. So I think generally the way to go is talk about power wasted being reduced. Okay.